Hello, good morning.
Good morning.
Good morning, Simona. How are you?
I'm fine.
That's the last day of the conference, probably tired.
A little bit.
A lot of work?
But it is a quite nice day, so.
Okay, good. Tell me, who are the participants? There are students from Lithuania or all over the place? That's the last day of the conference.
It's all over the place.
Okay, very nice. Can I just try to briefly to show my presentation, and then we can switch back to this screen that you have.
Adomas, can we?
If not, that's okay. I think it will work.
I think we could just in a minute.
Okay, no problem. And you mentioned I have between 30 and 40 minutes. This is okay?
Yeah.
Okay, good. I don't want to speak too long.
Yeah, and now you can share your screen.
Ah, thank you. Let's try. Does it work now? Is it full screen?
It is.
Okay, good. Then I'm stopping now. Okay.
Good morning, everyone. It's again me, Smana Bredokaite, the chief organizer of the Cyseni 2022 conference. This is our fourth and last day of the conference. Today we will have two key speakers, Wojciech Krolas and Darius Milčius. Let me introduce you to our today's first speaker, Wojciech Krolas. He is the professor at the Institute of Nuclear Physics of the Polish Academy of Science, Krakow. His background is in nuclear physics. He is involved in neutron science, an European research program on nuclear fusion. Since 2015, he is one on the design team of the fusion neutron laboratory IFMIF-DONES. And today he will present to us IFMIF-DONES, an accelerator-based fusion-like neutron source. Dear Krolas, screen is yours.
Good morning. Good morning, everyone, and thank you for this very kind introduction. Labas rytas, as you say, in Kaunas. Let me share my screen with the presentation. I hope you can see it well in the full screen mode. So it is a great pleasure to speak at this conference of young scientists on energy and natural sciences. And thank you very much to the organizers for their kind invitation, for giving me the opportunity to present the project on which I'm working, IFMIF-DONES, an accelerator-based fusion-like neutron source. And I'm especially thankful because this is a work of many institutes, including also our friends from Lithuania, from the Lithuanian Energy Institute, who are participating in this project. So first of all, I think I owe you an explanation what this acronym stands for. So IFMIF-DONES is International Fusion Materials Irradiation Facility, Demo-Oriented Neutron Source. I don't know if you know more after this explanation or less, but let's see if I can explain in the course of this presentation. So the plan is, I would like to put IFMIF-DONES in the framework, in the context of the European Fusion Research Program, say a few words about studies and validation of materials for the nuclear fusion program, present the concept and the present status of the design of IFMIF-DONES, and at the end mention something about other physics experiments which can be done at this facility. So Europe has a very ambitious research roadmap which should lead to the realization of energy from nuclear fusion. And the main facility, the main actor in this roadmap is the ITER reactor, which we all know. It is an international project under construction in Cadarache in France. ITER will be followed, ITER will be a research reactor. It will be followed in some 20 years, perhaps, by the so-called demonstration power plant, which will be optimized for energy production, to prove that energy production to the electrical grid is possible. And then there is the third link, the third part of this program, which are the materials needed for the development of such powerful reactor. And this is where the IFMIF-DONES facility comes in. So it is part of the European research roadmap for the fusion energy realization. The material irradiation is very important in all this. And the strategy is that of course, we are doing a lot of material studies in test reactors, and there are databases of material properties being built. The problem with them is that conditions in a reactor do not reproduce those which are present in fusion environment. So you know the physics of it. We have fission, we have neutrons of, on the average, lower energies produced in fission of heavy elements, while in fusion and deuterium plus tritium fusion is the reaction of choice for the production of energy for many reasons. Most of the energy is carried away by very energetic neutrons, by fast neutrons of 14 MeV, and also helium is produced and carries away some energy. So what we need is fusion-like irradiations, and here is IFMIF-DONES that steps in. So we need a facility for material qualification, which reproduces this 14 MeV neutron flux and reasonably high irradiation volume, high flux, and also a good control of the temperature in order to validate the materials for the fusion reactors. Some spectrum, some plots, some information. Here are the spectra of the neutrons from different sources. So let's start with the reactor. The blue curve is the high flux reactor, grid. So this is already a fast neutron reactor, and you see the spectrum. Well, kind of goes down here between 1 and 10 MeV. The European spallation source will have a very flat neutron spectrum here, also going up to higher energies, but rather continuous. This will be the spectrum of neutrons in ITER, the purple curve. And as you see, there is a distinct peak at 14 MeV energy. Now with IFMIF, we are coming as close as possible. This is the black curve to this neutron spectrum here, with a large portion of the neutrons coming in their energy range between 10 and 40, 50 MeV. So, what properties of materials should we study in order to be able to use them to build a fusion reactor? Well, we want to study some structural materials, very easy structural materials such as steel, tungsten, copper, and look at such properties, such effects like swelling, radiation hardening, embrittlement, and also functional materials which will be subjected to large radiation doses, in which other effects can take place, such as electrical degradation, reflectivity, and other things. And now I will make a very short overview of what is expected. So displacement damage, this is what happens. You have a neutron coming into a material, let it be steel, and it displaces an atom. It is called, the atom that is kicked out of its position is called the primary knock-on atom. And it transfers some energy, and the pKa can dislocate more lattice atoms, make a damage cascade. What is left afterwards are some vacancies in the lattice, and perhaps also some so-called self-interstitial atoms, so atoms which are sitting in the wrong place. This changes, this is microscopic picture, what is happening, but it also changes the macroscopic properties of the material. The keyword here in the science is dPa, which is displacement per atom. This means how many atoms, how many times has one atom been kicked out of its original position. It doesn't mean that this was a surviving effect. It can go back to its position, but this is how many times it got hit by the neutron or by a secondary product of such a reaction. And so this is the keyword. Transmutation is what happens when nuclear reactions take place. Of course, they can also take place in case you have such high energetic particles, like 40 MeV neutrons. And in that case, new elements are being produced. And this, of course, changes the properties of the materials once you have new elements introduced where they were not supposed to be originally. What is different as compared to fission? Well, in fission, you also have neutrons which can make damage to the materials, but the cascades are much smaller, much shorter, because of the smaller energy of the neutrons on the average. In fusion, this is a huge difference. The recoil cascades are much larger, the effect is much stronger. Another point that is different here when you have high energy neutrons in fusion, also helium can be produced in nuclear reactions. And this is a cross-section for production of helium by neutrons in iron. And as you see, this reaction sets on around 5-6 MeV. It will not take place in a fission reactor. And this is very important because eventually a high production of helium in steel will lead to creation of sort of helium bubbles within the material. And this deteriorates the macroscopic properties of the material. Well, this is very interesting. Irradiation embrittlement. So let me try to explain it briefly. You have materials which are ductile, which means that they are plastic, and also materials which are brittle. You subject it to a force and they break. And this curve should be seen from the right to the left. Let's look at the gray curve first. This ductile to brittle transition, this is the energy which the material can take. And for some Eurofer, for some steel, this is fairly flat if the material is not irradiated until some low temperature around -90 degrees, when suddenly the steel becomes brittle. Instead of being ductile, it becomes brittle. And we know it. If you put a piece of steel or plastic or whatever in a liquid nitrogen, it will become brittle. You can break it easily. Now, let's look at what happens when we irradiate that material. The irradiation causes microscopic changes, and on the macroscopic level, this leads to a change of this, a very large, significant change of this temperature. First of all, the level here, energy level, which can be absorbed, is lower, so they are less. These materials can take less energy before showing an effect. And second, this temperature changes. So already around 100 Celsius, the material becomes brittle. So this is very important, and one must know about it, and one must know about it in a very detailed and qualitative way to be able to design anything which will be able to withstand such irradiation. This is a very large dose, 32 displacement per atom. So a very high dose has been given to this piece of material. Another effect, this is very this is quite impressive, is the swelling. So increase of volume. For some materials, when you give enough radiation dose, you will see that due to the changes in the lattice, the volume, the size of the piece of material will increase. This is due to the condensation of vacancies left in lattice, and they merge into voids. And as you can see on this plot, there is an incubation time, and then depending on the fluence or the radiation dose, you will have the increase of the size. And finally, another property, this is more of a functional material. Conductors or insulators are subject to changes of electrical conductivity when subjected to irradiation. And there can be so-called radiation-induced conductivity, which is instantaneous. It comes when additional electrons are excited to the conduction band, and also some permanent degradation which can take place. And so again, a very important thing, you have your insulator somewhere close to the first wall of the reactor, and suddenly after some dose or linearly coming up linearly with the dose, it starts to conduct some current. It's not an insulator anymore. So back to our fusion devices. why do we need to study this materials? Because we already have tokamaks working. The point is that in the existing tokamaks and also in ITER under construction, the dose rates expected on the first wall are fairly small, up to 2 displacement per atom for the full lifetime of the facility. Now, the demo reactor is designed in such a way that after 5 years of running, it can accumulate over 30 dPa. And in fact, there is no systematic data above that value. So we need to study the materials, and as I said, steel, structural materials, tungsten, copper, and whatever is needed here. So now I'm going to the IFMIF-DONES program. So this is the program to build the facility to do the studies, and it's a long program. It started around the turn of the century, and first it was has been realized in collaboration with Japan. It's called broader approach. Collaboration of EU with Japan, and some important validation activities have been done in Japan. I will show some pictures later. The main phase, and I'm working in this phase, is the design and engineering phase, which is done in the framework of the early neutron source work package of the Eurofusion Consortium. This is a consortium which involves 14 countries, research institutes all over Europe, also in Lithuania, in Latvia, in Poland, and up to 100 researchers, engineers in institutes and also in industry are working on this. Other things, well, the site selection process is important. The site of IFMIF-DONES will be Escuzar, which is near Granada in Spain. The lifetime of the facility is designed for 30 years of operation. And the start of operation, it will be hopefully at the beginning of 2030s. I will show more about this. The concept is very simple. It will be an accelerator-based neutron source, which means that the neutrons will be produced in reactions with a beam of deuterium of 40 MeV energy, stripping reactions of deuterium on lithium target. What is unusual here is not the deuterium beam at 40 MeV, because this is easily done at many accelerators, but the very high intensity which is needed to produce a high flux of neutrons. High intensity means also high power of the beam, which is 5 megawatts. So the target cannot be a fixed lithium target, and it will be a flowing carton of liquid lithium. Lithium is a metal which is liquid at temperatures above 200 Celsius, and we will have a nicely shaped flow of lithium where the reactions will take place and they will produce neutrons. This is a reaction we produce a lot of neutrons with the proper energy, and behind the target irradiation module will be placed with samples that will be irradiated with neutrons with very, very high neutron fluence. So we'll be able to achieve 20 to 50 dPa dose rates in 1 year of irradiation in a fairly sizable volume of the irradiation. This is how it is done. Well, this is the plant configuration. It's all described fairly nicely in the documentation. We have a preliminary engineering design published. So the accelerator is composed of several components. Then we have the lithium system, the irradiation system here. And of course, there's a lot of supporting systems in the facility, such as electrical power supply, heat rejection, and so on, remote handling of some pieces, and also the instrumentation and control system. The accelerator is a very demanding facility because of this high current, because of very high requirement to have a continuous wave operation with a high availability. And it's composed of the ion source, RFQ, and a superconductive liniac with an RF source. It is also very interesting that we, the high energy beam transport line, which happens here at 40 MeV energy, is designed in such a way that we have a flexibility to have different beam footprints. All these 5 megawatts of beam power cannot be brought onto the target in a pencil-like beam. So we will have the beam defocused into either 20 by 5 centimeters footprint or 10 by 5 centimeters footprint, which of course will have an effect on the irradiation volume, on the volume which receives the high dose behind the target. So we can tune it in such a way that we can have higher volume but less dPA, or a larger volume with a larger dose. So this is the 3D model of the accelerator, and the most problematic part, of course, is the high power and also high charge effect in the low energy part. And as I mentioned before, there are some validation activities which have been going on in Japan. And actually, there is a prototype of the low energy part of this accelerating being built now in Rokasho in Japan. And this is, most of the pieces are designed and manufactured in Europe by those institutes, but they are assembled and tested there in Japan. So this only goes to 9 MeV, not 40 MeV. And we have very good results from Rokasho. We have already the full current, which is needed, 125 milliamps. Transmitted through the RFQ with very high efficiency, so everything is good. It is still in pulsed mode. It has to be changed to continuous wave, and then there is another LINIAC module coming, but this is all being going on, and the results are very promising. Now about the target. The target is very, very interesting liquid metal technology. We have several laboratories working on it, including our friends from Riga, from Latvia. Here is the target itself, but you see the lithium loop is much larger. First of all, it contains the heat exchange loops, because the lithium carries away this 5 megawatt energy to a large extent. The volume of all lithium is about 8 cubic meters. And the temperature of the operation will be around 300 degrees Celsius. One very important thing is that in the reactions taking place in lithium, we will have some impurities being produced, which are very dangerous and unwanted. And most tricky elements are tritium and beryllium. So we have to manage very carefully this impurity. There is a purification loop here where specially designed traps are used to trap hydrogen, so tritium, and also other products, in order to assure that we have a clean lithium circulating. The target is here. Lithium will come from this direction. Here will be the beam. And the jet of lithium will be shaped in such a way that it's 25 millimeters thick, with high velocity. Why this thickness? This thickness assures that all of 30 MeV neutrons are stopped in the lithium. We want only neutrons on the other side, and the neutrons will be fully stopped, giving up their energy to lithium. Again, about 10 years ago, there was a validation activity in Japan, and a test lithium loop has been built in Orai. It has been used only for 1 month, but it has proven that such a stable flow that we need with a nice nominal thickness can be achieved. This, what you see here, is simply flowing metal, which is properly shaped. Okay, this loop unfortunately is now dismantled, so we cannot use it anymore for testing. And then we come to the tests or irradiation system, so the heart of the facility. Heart of DONES will be the so-called test cell, where we have this lithium target I described in a moment before, and behind it will be placed the test module, the high flux test module, and it will contain here the samples. Apart from the high flux test module, we also are designing a dedicated startup and monitoring module, which will be placed in the same place before the irradiation, with a lot of sensors, different sensors for neutrons, gamma radiation, to characterize in an exact way the field that is the radiation field that is in the position where the samples will be placed. The high flux test module itself, this is how it looks. This is the most important central part, the container. It will hold capsules with samples. And for such studies, we use the so-called small sample test technology, where you have miniature samples. This is the size, which are shaped in such a way that you can study macroscopic properties of the materials, so fatigue, bend toughness, crack growth, and so on. This is the active volume, about ½ liter. And also that it is very important to say that those samples have to be kept in stable conditions, stable and controlled conditions, so they will be heated to the given temperature, then they will be cooled with circulating helium when the nuclear heating sets in, and so on. So this is a central part of this facility. All right, going to the last topic, there has been a large movement to consider IFMIF-DONES as a place where other experiments, physics experiments, can be done. There's a lot of interest because it will be a unique source of fast neutrons, and different areas have been considered: nuclear physics, basic physics studies, medical applications, and industrial applications, and so on. The assumption here is that the facility will mainly work for fusion, but complementary experiments can be run in the so-called parasitic mode, not affecting the main mission. And so since now IFMIF-DONES has been acknowledged by the European Strategy Forum on Research Infrastructure, ESFRI, as a strategic project in the energy domain for Europe, there has been some development and a program to develop those complementary experiments. It was called DONES preparatory phase. First of all, this is the facility. This is the test cell where the irradiation will take place. And we have a hall for experiments with neutrons, which is behind. So this wall, which is a very thick shielding wall, will have a neutron transport line with a collimator, with a so-called a neutron shutter, which can be opened and closed. And the flux will be transported to this room where different experiments can be run. Experiments using neutrons. The neutron flux behind the module, this is the target, this is the module, is still very large. So it is changed a bit and a bit moderated, of course, but still very adequate for physics experiments. And we are modeling the radiation conditions in this room and analyze different experiments to see their feasibility. Other option being considered is the application of different modules behind the high flux test module. So for instance, modules for the production of radioisotopes are also possible. Another option is to extract a fraction of the neutron beam from the accelerator. It can be done here at the high energy beam transport line using a setup of beam optics that I will not discuss. In such a way, you can steal maybe 1%, maybe 2% of the beam and send it to a different facility. There is a space reservation here in the floor underneath the accelerator, and produce neutrons on another production target, for instance, beryllium or graphite. And in that case, those neutrons will be produced in a pulsed way because you deflect the fraction of the beam with some time characteristics. And this could be turned into a facility very similar to NTOF at CERN or Neutrons for Science at Guernsey. These are the facilities where you do experiments with neutrons, with the known energy, and there is a lot of demand of beam time for such experiments. And we are considering, this is not implemented yet, to build such a facility in the basement of IFMIF-DONES. So, let me come to some summary. We have a consolidated design of IFMIF-DONES. It's ready for construction. There are negotiations with countries who are interested in the participation. The host country, Spain, also Croatia is involved because it was a common proposal, and other countries are joining in negotiation. Now the site in Escuzar, Spain has been characterized. It already belongs to the DONES consortium, and the licensing, radiological licensing and environmental procedures have been started. There is a technical project office already established. It is hiring if you are interested. And already this year, the first three buildings, some warehouses, administration building, and so on, have been the construction has been started, and we also started the installation of some support labs. So this is Grenada, at the other end of Europe, if I may say so. There are also considerations about the complementary science. So there is a user community interested in this program at IFMIF-DONES, and in fact, in September, we'll have the first users workshop to build up that community. A review will be made how to implement, which experiments should be implemented. And if you would like more information, this is the website of IFMIF-DONES, and two papers which contain a short account of this program. And in the end, let me summarize. This is what we want. This is the fusion power plant, tokamak, which produces energy to the grid. We know that fusion can be done. Well, ITER will answer if it can be done with the proper power. Demo will answer if the fusion is feasible, and fusion power plant will provide a commercial application of fusion. To make way for this, we need IFMIF-DONES, because it will extend the existing knowledge of the materials in harsh radiation conditions. This is not only research, as I must say, not only knowledge about what materials, how materials behave, but if you want to apply for a licensing of a fusion power plant or even a demo, you need to have databases and really validated information, which is good enough to go to a regulatory body to present, to prove that these materials can withstand the doses expected over the lifetime of the reactor. So IFMIF-DONES has been designed for that, and along the way, we are developing a lot of new exciting technologies which are needed for this facility. So thank you very much for your attention. I hope there will be some questions which I can answer.
Thank you, Carlos. It was really a pleasure to listen to you, to hear that much information. And it is my first work was about IFMIF-DONES, so it is really nice to hear about. My first question would be about COVID, how it changed plans for IFMIF-DONES.
Excuse me, about?
COVID-19, how it changed the plans?
It didn't change much, no. It made our work more difficult, but we continued our work. Maybe we gathered some delay because things have been more difficult. Travel to Japan has been stopped for 1 year, and also some laboratories, supporting laboratories, have been closed. So maybe it gave us 1 year of delay.
And what influence had the record of JET in your calculations and plans, or it doesn't have any? The new record of JET, the materials.
Yes, it is very interesting. I'm not sure if it it is of course being considered. I mean, this just encourages us to go forward with this program, because it is a very promising result from JET, and we it kind of confirms our conviction that that we should go forward with the materials program at DONES. Yes.
Yeah, so I think our participants had time to write questions, but I don't see any. So yeah, I want to say once again, thank you, Professor Krolas, for your presentation. It was really interesting.
Thank you very much. It was a pleasure. Thank you.
I hope we see each other live.
Absolutely. Thank you, and good luck with the rest of the conference. Thank you.
Thank you. So, dear participants, now we have a little break until 11 a.m. in Eastern European summertime. So yeah, grab a coffee, take your break, and we will see in 25 minutes with our second presenter. So welcome back, everyone. Now is time for our last but not least key speaker. It is Darius Milčius. He is head of Center for Hydrogen Energy Technologies at Lithuania Energy Institute. Since 2001, he is expert of one of the tasks in the International Energy Agency Hydrogen Implementing Agreement. He has been author or co-author of more than 40 publications on metal hybrids, 15 publications on solid oxide fuel cells. He also has developed 5 patents and applications at Lithuanian Patent Office, and he has many more achievements about which you can read in Cyseni page. And today he will talk about hydrogen technologies at Lithuania Energy Institute. Dear Milčius, the screen is yours.
Okay, can you hear me? Can you see me?
Yeah, we can.
Okay, thank you, Simona, for a nice introduction. Actually, I will try to share my screen. Let's move on. Yeah, okay. Can you see it?
Yeah, we can see it.
Okay. Okay. So thank you, organizers, one more time for the possibility to present our activities on hydrogen energy technologies at Lithuania Energy Institute. And actually, I'm representing Center for Hydrogen Energy Technologies here at the Institute. For those who don't know, just very brief information about the Institute. We are in Kaunas, in the middle of the country. This is red dot. In the middle, we have about 250 employees and lots of ongoing and already done project starting Horizon 2020 program and also Horizon Europe Now. We have 5 directions at the Institute. It's research on energy technologies, thermal engineering and metrology, environmental engineering, material science, energy systems, and economy. So hydrogen is split actually in all the directions. So you can have hydrogen in combustion processes and also in synthetic fuels, which represent in the area of research on energy technologies. Lots of is done on material science part. We are developing materials for hydrogen generation, storage, and also fuel cells. And we're also doing modeling on system level. I will present some our results on that topic. This is content of my talk. I will try from the modeling activities. We'll switch to the hydrogen for portable mobile application. Will represent our activities on development of solid state hydrogen storage materials. Our latest developments on hydrogen production as it needed, so-called aluminum hydrolysis processes. Also represent some latest results on metal hydrides for synthetic fuels and some ideas on demonstration sites, which we're developing here at the Institute. So let's start from the general information about the hydrogen. So hydrogen, as all of you know, it's a gas. The main challenge with hydrogen is related that it's impossible to find in Earth in free form. You need to have hydrocarbons such as methane, will be hydrogen and oxygen. And in case of hydrocarbons, it will be carbon particles or CO2 and hydrogen. So in order to produce hydrogen, one needs energy. So energy usually comes in the form of electricity or heat. So when we have green electricity, which is coming from biomass, hydro, wind, and solar, we have production of green hydrogen, for example, from water. When we use coal or natural gas, we use different processes. We produce so-called gray hydrogen, which in order to produce 1 kilogram of hydrogen, we also have 7 kilograms of CO2. So this is not clean hydrogen and not so attractive for the final user. So when you have hydrogen in the form of a gas, there is lots of possibilities to store it, to transport it, and to use in transportation and in distributed generation. Here you can see also few important numbers. This is price for 1 kilogram of hydrogen at the production site. So in case of green hydrogen, the price of green hydrogen today is from 4 to 6 euros per kilogram. And the price for gray hydrogen is 1.5, 2.5 euros per kilogram today. So talking about the hydrogen economy, it will be on the market when the price of green hydrogen will drop to the price of gray hydrogen. So we need new technology developments and we need new routes in equipment development in order to lower the hydrogen price from 4 to 6 euros per kilogram to almost 2 euros per kilogram. So let's move to the modeling system level and our activities on the subject. So as I told you previously, the best way to produce green hydrogen is to use renewables as initial electricity source, but also hydrogen could be used in order to connect with unstable renewables into the national or grid, or to produce the high quality electricity for final user. So when you have fields which are filled with the solar power plant, this is the example of 2 megawatt PV solar generation. It works usually very unstable. So you have peak somewhere in the middle of the day, but we have lots of fluctuation during the generation time. So in order to somehow to balance this fluctuation, you need intermediate energy storage devices which can absorb produced electricity and to submit high quality electricity to a final user. So which methods could be used for electricity storage? So there are lots of possibilities, and there are storage technologies which are based on mechanical, electrochemical, electrical, and chemical principles. If you need to store a small amount of electricity, let's say less than 1 kilowatt hour, so you can use capacitors and supercapacitors. If the amount of electricity which you would like to store increases, you can use flywheel energy storage systems, and of course lots of batteries, starting from lead-acid batteries and going to the most advanced lithium-ion batteries. Pumped hydro is also very attractive methods for electricity storage and for use together with unstable renewables and hydrogen. If you look to the hydrogen, it's most versatile energy storage media. So you can store electricity from 1 megawatt hour up to few terawatt hours. And there are systems where not represented here where you can store less than 1 kilowatt hour using hydrogen technologies. If you look to the left side, so-called release time, you can see main benefit of hydrogen. So instead of storing it only for a few hours, as in case of batteries, you can store electricity even for a few years. So what does it mean? It means that if you produce lots of electricity during the summertime, you can use it for hydrogen production, and hydrogen could be stored up to winter time, and you can convert it back to the electricity and to the heat. So this means that instead of storage for a few hours, you have storage between the seasons. So this is one of the greatest benefits of the use of hydrogen for energy storage. So this is our developments on modeling. We just finished the Horizon 2020 program project, so-called iDistributed PV. And here we developed a special software which allows us to calculate lots of scenarios which are related to the end user and also shared generation technologies and also shared storage technologies. All of these technologies could be connected to the national grid or to the local grid in order to sell electricity when we have access and to buy when we need it. So all these facilities could be connected to end user, and end user can have the consumption profiles, and these consumption profiles could be matched with the production and storage profiles. This is examples. So here you can see the early radiation in Kaunas in Lithuania, and on the left side you can see the early demand of a studied prosumer in Kaunas in Lithuania. So actually this is our institute, and this is our consumption on the minute resolution during one year time. So we combine these two data in our software, and we can calculate which installed power is more efficient in terms of payback time and also in terms of fed-in energy losses. So we can estimate how big our solar plant could be in order to have the minimum payback time, for example. We can connect different storage technologies starting from batteries and going to the hydrogen and try to evaluate how free we will become, independent free we can become from the national grid. And actually, when we're talking about additional storage technologies, so these numbers which are related to the payback time increases radically today. So this means that we need lots of technological developments in order to decrease hydrogen technology price. So let's move to the technological part, and this is hydrogen for portable and mobile application and development of solid-state hydrogen storage materials. Before switching to materials, let's talk a little bit about use of hydrogen and production of hydrogen for the vehicles applications. There are two possibilities. So first possibility, we have unstable hydrogen electricity generation, which could be a wind energy farm. It generates electricity. We have water electrolysis. We split water into the hydrogen and oxygen. Oxygen goes to the market, and hydrogen goes into the storage system or goes to the transportation system, and it's filled up into the vehicle tank. So when we have hydrogen inside the vehicle, we can use fuel cells and produce electricity. And actually we have electrical vehicles, but instead of batteries, the energy is stored in the hydrogen form. So all these technologies has lots of different steps, starting from electrolysis, storage, transportation, fuel cells. So the efficiency drops. So talking about general efficiency of this path, we have 30%. So when we produce 1 kilowatt hour here at the wind power plant, and when we consume it in the vehicle, we have only the 30% of that. This is comparable with internal combustion engines, but not comparable with the battery vehicles. Another direction which could be used for the hydrogen in the vehicle is related to the production of synthetic natural gas in compressed natural gas vehicles. So the beginning of the technology is the same. We have unstable electricity, we produce hydrogen, and after that, we have special equipment which can extract CO2 from air or from biogas, and we can combine CO2 and hydrogen in special equipment, and we can produce synthetic CH4, which is synthetic methane. So this methane could be used for vehicle applications. So you see the number of technological steps increases radically, and the efficiency decreases too. We have only about 10% of efficiency here in the wheels. Let's combine different energy storage technologies. So this is diesel, compressed natural gas, compressed hydrogen, and lithium-ion batteries. So all of these energy storage technologies could be used in light vehicles in order to go 500 kilometers range. So if we look to all possibilities precisely, we of course can say that the diesel is most efficient one in terms of weight and volume. However, it produces lots of CO2. So we would like to escape from CO2 nowadays. So maybe we can replace it using batteries or using compressed natural gas. So in order to go 500 kilometers, we need about 6 kilograms of pure hydrogen. So this hydrogen could be placed in the system, which is 125 kilograms in weight and 260 liters. If we try to compare this system with lithium-ion batteries, you can see that this is much lighter and less in space. But of course, if you try to compare it with a diesel energy storage system, you can see that the diesel is far better than the hydrogen. Talking about hydrogen, there is also a very important challenge which is related to the pressure. We need 700 bars. So lots of solutions and let's say interesting and expensive compression system could be applied in order to fill up the hydrogen vehicle. This is how it looks like in reality. The blue one, it's 6 kilograms of hydrogen at atmospheric pressure and room temperature. When we pressurize it up to 200 bars, so it looks like this. It could be liquefied, it looks like this, and stored in the different solid state hydrogen storage materials. So here you can see magnesium to nickel MH4 and lanthanum nickel MH6. And this is gasoline tank, our usual tank, which we have in our cars nowadays. So what we can say about these storage methods. So if you to compare volume, the solid state hydrogen storage materials wins over the pressurized systems. But the pressurized systems are light and metal hydride systems are quite heavy. So this is also, we can compare the filling up time. So in case of pressurized systems, we need about 10 minutes. In case of metal hydrides, we need more than 15 minutes in order to fill up the tank. So there are lots of challenges and positive things about hydrogen storage technologies, and we will go in depth in a few following slides. So let's compare storage. So physical storage methods, actually, which represent pressurized hydrogen and liquefied hydrogen. So here you can see the hydrogen pressure at atmospheric conditions. So at 1 bar of pressure, we can store about 0.3 grams per liter of hydrogen. We can pressurize this hydrogen up to 700 bars, and we will have up to 40 grams per liter of stored hydrogen. If we liquefied hydrogen, we have about twice of hydrogen stored, actually 71 grams of hydrogen per liter. But the challenge in this technological solution is the temperature. The temperature is very low, it's around 20 kelvins. So this means that in order to store hydrogen in liquefied form, we need to cool down it using liquid helium technologies, which is rather expensive ones. Let's move to a material-based hydrogen storage. There are lots of possibilities. It is interstitial hydrides, complex hydride, chemical storage system, for example, such as ammonium, and different sorbents, such as metal framework systems, and also with water. It's also a good place for the hydrogen, to store hydrogen. If we try to combine the gravimetric capacity of interstitial hydrides, for example, with pressurized systems, we can see that in case of interstitial hydrides, we have something like 4 times more of hydrogen, which is stored in the same volumetric density, 1 liter. But there are lots of challenges with the solid state hydrogen storage materials. Let's come back to some calculations which was done by Department of Energy of United States, and they made lots of technological and economical calculations and came to conclusion that if we have hydrogen storage system which can store up to 68% of hydrogen with a volumetric density around 40 grams of hydrogen per liter, this car is can compete with the internal combustion engine. Actually, if we try to compare existing hydrogen storage system at the market, such as liquefied hydrogen, compressed hydrogen, and chemical hydrides, complex hydrides, we can see that all of these storage methods are lower than 68%. In case of liquefied hydrogen, we have something like 5% of hydrogen. And in case of complex metal hydrides on industry level, have only 2 weight percent and 20 grams per liter of hydrogen. So try to remember this 6 weight percent of hydrogen and 40 grams per liter. And this is this yellow dot here, 6 weight percent and 40 grams per liter. So as you can see here, there are lots of metal hydrides which exceeds these numbers. Let's take example of magnesium hydride, which is very simple hydride. It can store up to 7.6 weight percent of hydrogen, and also volumetric capacity is very nice. It's about 110 of grams per liter. Looks good, looks very promising. However, there are lots of challenges. So first challenge is related to the temperature. So as you can see, in order to fill up such type of material and in order to form magnesium hydride, you need to heat up it more than 300 degrees. And also to release the hydrogen, you need to even more heat in order to decompose magnesium hydride to pure magnesium and to the hydrogen. A part of these high temperature requirements, there are also lots of problems or challenges which are related to the reversibility of the materials and the kinetics of hydrogen metal hydrides formation, which are where in case of kinetics is very slow. In case of reversibility, it's not so easy to prepare the material which can withstand, for example, 1000 cycles without minimal losses. There are very attractive metal hydrides, such as lithium boron hydride, which can store up to 18% of hydrogen on the materials level with very high volumetric density. However, if to keep these materials in the vehicles, actually, when we decompose lithium boron hydride to come back to lithium boron hydride back, actually it's impossible on board. So you must remove the lithium boron hydride after decomposition and try to make lots of chemical steps in order to come back to hydrogen storage material. So this is very challenging one. So why we have problems with solid state hydrogen storage materials? So here you can see the system where gray balls represent the metal. It could be, for example, magnesium, and red ones, it's hydrogen gas in the form of molecules. So hydrogen gas in the form of molecules can't react directly with the metal matrix. So you need to split hydrogen molecule into the atoms. So in order to do this, you need some catalytic particles on the surface, and usually this is palladium or platinum. And that makes solid state hydrogen storage not so attractive for the industry. Why? Because when we increase the use of palladium and platinum due to the limited resources on Earth, the price of these materials increases dramatically. So let's try to imagine that we have some catalytic particles on the surface. So hydrogen molecule coming, splitting into the atoms, and these atoms can easily go into the bulk of the material and form solid solution at the beginning. And with the increase of hydrogen atoms into the bulk of the material, we can see formation of metal hydrides. Our activities, let's say, are split in two directions in the lab. We are trying to work on thin film, so-called 2D materials, and this is our activities on magnesium to nickel MH4. We produce magnesium to nickel on thin films, and we have different hydrogenation approaches, and we can produce metal hydrides in different crystalline forms, in low temperature form, so-called monoclinic magnesium to nickel MH4, and also high temperature form, which is cubic magnesium to nickel MH4. So when we talk about cubic magnesium to nickel MH4, you see this origin code, and the response change is colored by applying different temperature regimes at different stages. So part of hydrogen material is used as supplement of switchable mirror devices. So additionalities to these hydrogen storage materials. Our research on powders, which is more application-related technology. If you remember my previous few slides, so I told you that we have challenge with splitting our hydrogen molecules, and we need additional catalyst on the surface. So we are trying to develop technologies and to escape from the need of palladium and platinum, and we developed the hydrogenation technology, which is based on immersion of materials which can absorb hydrogen into the hydrogen plasma. So instead of expensive palladium and platinum, we use electricity and we produce plasma. And in plasma, we have splitting of molecules into the atoms. Atoms could be ionized to the ions, and these particles could go to the near surface region, form hydrogen saturation surface, and with the increase of hydrogen concentration in near surface, hydrogen goes into the bulk of the material, form compressive stresses, and we have formation of solid solution, and with the increase of amount of hydrogen, formation of metal hydrides. All of this very well described in our patent, which was granted by European Patent Office few years ago, and we're still using this technology in our daily activities. A part of application-related developments, we're also trying to make lots of fundamental research, and we are studying adsorption, desorption, absorption, activation of surface, different surfaces, also surface cleaning effects and chemical reactions on the surface. And here you can see examples of quantum mechanical modeling, which was done by using stream code, where we immerse our hydrogen absorbent material, in this case is magnesium to nickel, and hydrogen ions penetrates in near surface region up to 20 angstroms in the depth, and we have activated layer on the top of our material, which we would like to enrich at high temperature and high pressure. So this is the results of hydrogen materials activation. So this is initial powder. We are trying to keep it in hydrogen atmosphere in the form of powders. And as you can see, after 2 hours, we still do not have proper saturation. And in case of activated materials, but the kinetics of hydrogen adsorption in near surface region and absorption in the bulk increases dramatically. So this technology might have some future applications in hydrogenation and production of suitable metal hydrides. So when we start our activities on metals activation using plasma approach, we also find that this activation approach could be used for the activation of aluminum. And when we have active aluminum, it could be immersed into the water, and we have, after the chemical reactions, we have production of hydrogen, production of some heat, and also production of some byproducts. And here's the example. You can see the work of our colleagues at Massachusetts Technological Institute, and they produced the aluminum hydrolysis part, so-called hydrogen production as it needed for autonomous undersea vehicles. So aluminum hydrolysis in more details. Let's say we have 1 kilogram of hydrogen and 2 kilograms of water. Aluminum is activated. Lots of technologies possible, starting from ball milling, going to, let's say, another mechanical treatments. And if we have alkaline water, we can immerse aluminum into alkaline water, and we can produce 11 grams of hydrogen, which could be used for electricity production, and we can produce 2.2 kilowatt hours of electricity. Lots of heat is coming out in both processes. Starting from hydrogen production, we have 4.3 kilowatt hours of heat, and from the fuel cells also heat is emerging. So lots of heat is coming from these reactions. Additionally to that, we have byproducts in the form of aluminum hydroxides, which could be converted to the gamma aluminum oxide. So this is how it looks like for the application side. So there is possibility to have tank, immerse activated aluminum into the water, and to produce electricity and power up laptop computer. for example. So talking about aluminum reactions with water, there is 3 stages. So first stage, the beginning of reactions. So water should reach the pure aluminum side, and after when it reaches pure aluminum side, the fast reaction starts, and we have most of the hydrogen produced. And the first stage, when we have slow reactions, so the remaining aluminum reacts with water, and we have production of small amounts of hydrogen. So that is the most challenging part in this technology. So this is related to the natural aluminum oxide layer on the surface of every aluminum particle. So here you can see aluminum particle, and if you extract it into the air, you have immediately formation of natural aluminum oxide, which is from 3 to 5 nanometers, and this aluminum oxide is one of the most stable oxides in the nature. So in order to have direct reactions of aluminum with water, you need somehow to destroy or modify this aluminum oxide layer in order to water to penetrate into the bulk of the material and have direct reactions with pure aluminum. So we developed the plasma activation technology. So we insert hydrogen ions in this near surface region, and actually we form saturated region, which is altered layer. So aluminum oxide, instead of uniform layer, becomes altered, and this altered layer allows water to go directly from the surface into the bulk material. And then reactions actually starts less than in 1 minute, and we have formation of hydrogen, which could be used in fuel cells, and formation of hydroxides, which later could be converted into the gamma aluminum oxide. Our latest development, we found that there is some thermal routes when we have plasma activated aluminum and we immerse it into the water, and after that we have formation of byproducts. There is possibility to heat up them and have production of gamma aluminum oxide, which is very valuable product and could be sold on the market for different applications, starting from the additives for civil building materials and going till the biocompatible materials, which are rather expensive ones. We also tested these hydrogen generation reactions via hydrolysis processes for magnesium to nickel and magnesium to nickel H4 powders. So we produce magnesium to nickel H4 using our plasma-based technologies, and these materials are very active. There is actually no need of alkaline or acid solutions. You can have tap water. You can immerse it in our activated materials into water, and as you can see, we can have stable hydrogen production for up to 9 minutes. So one of the last part of my talk is related to hydrogen hydrides for synthetic fuels. And when we talk about metal hydrides for synthetic fuels, let's talk a little bit about methanation processes. So when we have green hydrogen and CO2, which can come from atmosphere or biogas plant, we can combine these materials on the catalyst surfaces in methanation reactions, and we can produce synthetic methane, which could be used in vehicles. And here we have the neutral gas as energy source for a vehicle. So usually when this technology could be applied, for example, in biogas technologies. So in biogas, we have low CO2 levels and low CH4 levels and high CO2 levels. So CO2 could be combined with the hydrogen, with the green hydrogen on different catalyst materials, and we have can have formation of CH4 and water vapor. So actually we are doing this work here in our lab in collaboration with our laboratories. So we have magnesium to nickel H4, which serves as a catalyst and also as additional source of hydrogen, and we combine it with CO2 and we have production of CH4 and also production of carbon particles in the chamber. So this is one of the ways to escape from expensive palladium and nickel, and instead of that, to use instead of these materials, to use not so expensive magnesium to nickel H4. Last slide of my presentation is related to a demonstration site. So just very briefly, so part with activities on nanoscale, let's say on development of different materials, we are also trying to make our institute as energy island, independent energy island. So we installing PV power plants at the moment. It will go up to 1 megawatt in the future. Now it will be 500 kilowatts. And all this electricity could be used for the hydrogen production using water electrolysis processes. And hydrogen produced could be stored from the summer to the winter time, and could be used also for the transportation for fuel cells vehicles, and also for the production of synthetic fuels. This project is rather big. We are going to produce up to 200 kilograms of hydrogen per day, with a price about 2.5 euros per kilogram of hydrogen. So it will be, we expect it will be rather efficient thing. However, talking about possibility to get finances from a government, we're not so successful at the moment, but believe it will be better in the future. So that is the biggest benefit of this demonstration site. First of all, it gives possibility for the industry to know hydrogen technologies in more details, and also for the people to accept these new technologies and to become familiar with that, attract new students in studies processes, and to prepare new engineers for upcoming future. So thank you for your attention. So this is my talk.
Again, thank you, Darius, for your presentations. I think Lithuania Energy Institute have representative video about this green village of ours in YouTube. So please check it if it is interesting to you. As I can see, we don't have any questions, so everyone understands everything. So it's really nice to hear about processes of hydrogen. So thank you very much, Darius. Thank you that you agreed to represent our institute. And now some information before closing the session. I would like to remind all of you, that at 12 Eastern European time, we have energy science poster section in Gather Town. So go, please look all your colleagues' presentations and don't be afraid to ask questions. So thank you, everyone, and I hope we will see you next year in our conference